Okay, so to begin in this video, we're going to be deriving the hydrostatic pressure equation, which gives us the pressure distribution in a static fluid. So to begin, we're going to start with some key assumptions here. One, we're going to look at a differential element of mass, dm equals rho dv, where dm is the differential mass and dv is the differential volume. The element is static, so again, we're examining a static fluid. The only surface forces present are those of pressure, not shear stress, because shear stress is only present in a moving fluid, or in fluid dynamics, not fluid statics. And again, the element is differential in size, so it's infinitesimally small. We're going to assume that gravity is the only body force, so there's no magnetic field, there's no electric field, etc. And we're going to assume that our element is cubic in geometry. So if we look here to the left, we'll see that we have a global coordinate system, x, y, and z, and a local coordinate system that's attached to the cube that we're looking at, x hat, y hat, and z hat. You'll also see that gravity is vertically downwards, and our element is of thickness dy, dx, and dz. So to begin, what we really want to do here is look at what the total differential force on this cube is, which is equal to the sum of the differential body force plus the differential surface force. So it's easiest, I think, to start with the differential body force. So let's begin with that. Okay, so to start with our differential body force, we'll write dFB vectorized is equal to negative dm g k hat, where k hat is our unit vector in the z direction. That's equal to negative rho dv g k hat. Since we have a cubic geometry, we can write that dv is equal to dx, dy, dz. And it's common to collapse this negative sign and this unit vector k hat into g. So the way we would write that is we would say rho dx, dy, dz times the quantity negative g k hat. And we would write that as rho dx, dy, dz, g as a vector, right? G is a vector. So we can write that a little bit more conventionally as rho g vector dx, dy, dz. Okay, it's worth noting again that in a static or non-flowing fluid, there are no shear stresses. Shear stresses result from velocity gradients, for example, as you would see in Newton's law of viscosity, and here, the velocity throughout the entire flow field is zero. Therefore, the only surface force on the cube is that from pressure, not shear stress. So with that being said, we need to determine the pressure distribution in this flow field on this cube. And to do that, we're going to begin by creating a Taylor series for the pressure evaluated at this point right here in the middle of the cube, such that we could find the pressure on the left face, the pressure on the right face, the pressure on the top face, the pressure on the bottom face, the pressure on the front face, and the pressure on the back face. And remember, with the Taylor series, you need to evaluate it at a point, and we're going to choose to evaluate the pressure at the point in the middle of the cube. So let's write out the general form of our Taylor series, and we'll continue from there. So we have the general form of our Taylor series here in 3 dimensions, which basically says that a function at its general x, y, and z is equal to that function evaluated at some point of interest plus a bunch of combinations of its derivatives, right? So if you're not familiar with the Taylor series, I would encourage you to go familiarize yourself with that concept. But basically, this is the general form of our Taylor series to begin with. And we're going to write our pressure, P of x, y, z, in this Taylor series format. So again, we can get the pressure on the right face, the left face, top face, bottom face, etc. So let's write out our pressure as a Taylor series right now. So we're going to evaluate at this center point right here, which we'll call center point, CP. So we evaluate at CP, which is x hat equals dx over 2, y hat equals dy over 2, and z hat is equal to dz over 2, because that center point CP is right in the middle of that cube, and our local coordinate system x hat, y hat, and z hat is drawn such that it is originated at the innermost bottom vertex of this cube right here. So x hat goes positive here, y hat goes positive here, and z hat goes positive here. This center point CP is just dx over 2, dy over 2, dz over 2, just like that. So now we're actually ready to write out our Taylor series in earnest in terms of x hat, y hat, and z hat evaluated at this center point right here. So I'm going to write out that Taylor series for the pressure, and we will meet up at that point. Okay, so here's our Taylor series actually written out. So we have our P of x hat, y hat, z hat, and as you can see up here, the pressure is first evaluated at the evaluation point. So we evaluate the pressure at dx over 2, dy over 2, dz over 2, and then we just have a summation of partial derivatives of our pressure. So we have our x hat minus dx over 2 times the partial derivative of pressure with respect to x. We have plus y hat minus dy over 2 times the partial derivative of pressure with respect to y, etc., etc. It's worth noting that the partial derivatives are evaluated at the evaluation point. So dp dx, dp dy, dp dz, they're all evaluated at the center point as shown here. And then you have your remainder term right here. You could actually work out this remainder term. It ends up going on infinitely, technically. It is a function of the second order derivative, the third order derivative, the fourth order derivative, all the way up to the nth order derivative. It turns out at the end that these remainder terms end up canceling out, so I just collapse them into r. But you could work that out in theory and see for yourself that those terms cancel. However, we will get to that once we get further along in the derivation. So what we've fundamentally derived here is a function for the pressure in terms of x hat, y hat, and z hat. So what we can do then is write out what the pressure on this left face is and what the pressure on this right face is using this function right here. So let's look at P at x hat L, y hat L, and z hat L, where XL, YL, and ZL are just any points on this left face. And let's do the same thing for the right face. So we have x hat R, y hat R, and z hat R. And in a similar fashion, x hat R, y hat R, and z hat R are any points on this right face right here. So all we have to do is plug in these general coordinates into our Taylor series above, and then write out our expressions for the pressure on our left face and the pressure on our right face. So let's do that right now. Okay, so we have the pressures written out for our left face and our right face here. And there are a couple of notes to make. So first of all, I've dropped the notation here on the partial derivatives. You'll notice, or you'll remember that in our original Taylor series, our partial derivatives are evaluated at the center point, right? So even when we write out our pressure on the left face and our pressure on the right face, adhering to this above equation here, these partial derivatives are actually evaluated still at the center point. So dp dz here is equal to dp dz here. dp dy here is equal to dp dy here. dp dx here is equal to dp dx here. I'm going to just drop the notation to save space, but just know that these partial derivatives are equal to one another in both of these expressions. Second of all, I've notated the remainder term for the left face as r sub L and the remainder term for the right face as r sub R. And lastly, you'll see that our pressure evaluated at our evaluation point, dx over 2, dy over 2, dz over 2, is the same also in both of these expressions. We have a lot of common terms here, and we're going to see a lot of cancellations, and that works very much in our favor. So let's bring this on to the next page and start working out some of those cancellations. So now we're at a point where we want to use this pressure distribution on the left face of the cube and this pressure distribution on the right face of the cube to come up with an expression for the net surface force on the cube in the y direction. So if you go to the original cube and you discretize it into a bunch of little differential areas like this, then my intuition tells me that the pressure at this point is not going to be quite equal to the pressure at this point, or the pressure at this point, or the pressure at this point, etc. So all of these differential areas have slightly different pressures. So then I could say, hey, what happens if I take my pressure at this differential area, multiply it by my differential area, and then add it to my pressure at this differential area, multiply it by my differential area, and then add it to the pressure at this differential area, and multiply it by my differential area, and then just do that for every differential area on this left face, then that will yield me the total force on this left face. And then if I do the same thing on the right face, and then I add those results together, that'll give me the net force in y, right? The net force in y hat. They are aligned, so that they're essentially the same in this case. How am I going to add all of these differential products? I'm going to do that with an integral, a two-dimensional integral, because it's going to be over an area. So let's do that now. So here we have the integrals written out, and you'll notice that they're written as magnitudes. So here DFL is the magnitude of the force in the left face, DFR is the magnitude of the force in the right face, D is to represent that those forces are differential, and I have three different notations written out for the integrals here in each case, and depending on which textbook you're using, you may see any one of these, but they all mean the same thing, and it's essentially the same concept as we reviewed when we went back to this first cube here. We're just summing up the products of the pressures at each differential area multiplied by the differential area at that point. So again, the pressure at this differential area times this differential area plus the pressure at this differential area times this differential area plus the pressure at this differential area times this differential area summed up all over the face. The left face is DFL, and then correspondingly, we have the same case on the right face for DFR. Right? So we can write this as a single integral, so to speak, integrated over the area of PL times dA, or we can write it as a double integral here. You'll notice that the double integrals in terms of the local coordinate system, and that's x hat and z hat, over the bounds 0 to dx and 0 to dz. And that's because if you look at the original cube, you'll see that using those coordinates x hat and z hat, summing from 0 to dx is summing from here to here, and summing from 0 to dz is summing from here to here, which gives you this whole face. And on the right face, it's the same thing. Summing from 0 to dx gets you from here to here, and summing from 0 to dz gets you from here to here, which gives you this whole right face. And then finally, we have DFL minus DFR, the magnitude of the differential force on the left face minus the magnitude of the differential force on the right face. And that gets us our net force in the y or y hat direction. And since we are integrating with respect to the same variables and we are integrating over the same bounds, we can combine the integrals just like this, such that we have the double integral of PL minus PR. And this will give us the net force in the y and or y hat direction. Okay, and I think I'm going to wrap this video up because this is going to be a slightly protracted derivation. It's going to take a while. It's probably going to be 2 or 3 parts to it. And that's because this mathematical formalism, doing this derivation the mathy way, so to speak, is pretty long. It's pretty complex, but I do think it's worth it because using this mathematical thinking, this mathematical formalism, and some of these mathematical tools will pay dividends when we start deriving much more complex equations in the future that heavily rely on these mathematical arguments. But we will also review some of the more physical derivations of this equation using more physical intuition to get to the same final result. And we'll review those after the mathematical derivation has concluded. Okay, so thank you for watching. I really appreciate it. I will see you next time.